In this video, we give an algorithm to compute the arrangement of lines. The algorithm is essentially an incremental algorithm. We start with the initialization step where we initialize the bounding box and create an empty doubly connected edge list for the arrangement. How do we compute the bounding box? Well, that's actually not so hard. We can find all the intersection between the lines. We can just run two for loops, I equals 1 to n, j equals 1 to I minus 1, and then intersect the lines I and lines j to find the intersection point, or to find all the intersection point. Then we can compute the maximum x coordinate, maximum y, minimum x, and minimum y coordinate to build this bounding box that has all the intersection points of the lines inside it. After that, we have this initialization step done. Then we run a for loop, and at the ith iteration of the for loop, we insert line number I. And the way we insert line number I is as follows. We first find the segment of the bounding box intersected by the line L. Since I have n lines, or I lines, I minus 1 lines so far, there are only I segments on this bounding box. I just go through all of them, find which one intersect the line number I, then I have that intersection points covered. And essentially we do the same thing we did in the doubly connected edge list thing, where we have this face that is intersected by the line L. I just need to find which other edge of this face is intersected by line L. And I can do that by simply going around the face and finding the second intersection point. After I find the second intersection point, then I move to the next face, then I repeat. So essentially inside the for loop, after finding this initial edge, we have a while loop, that while we haven't exited, we haven't hit the other edge of the bounding box, we go through the faces and we find the exit. So in other words, while the f is not the unbounded face, split the current face into two faces and walk to the next face, right? So we walk this face to find this exit, then we walk this face, then we walk this face, and then this face, and so on. Okay. Splitting the face is not so difficult. We just have to create two new vertices and two new edges and set up the pointers. It's not super exciting. And then the running time. The running time analysis is not, giving some bound is not too difficult, but to get the best bound, we have to work harder. So this is where the non-interesting things, non-trivial things happen. So we can write the running time as n squared. So this is for the initialization step to find all the intersection points and the bounding box. Then we have a sum over the time that we need to insert the line number Li. A trivial bound for this insertion time is n squared, right? Because this while loop, through this while loop we go through n faces, right? A line can intersect n of the faces of the arrangement, and then each face could have complexity of linear size. So inside this we have n iterations. At each iteration we could walk through a face that has complexity n, so the while loop could have n squared time. So therefore the for loop could have n cubed time. Okay. That's obviously too much, and it's actually much slower than the sweep line approach that we had earlier. So the interesting that we're going to prove later is that the time it takes to insert line Li is actually linear. So therefore this for loop in total will take n squared time. To prove this, we define this notion of complexity of a zone. So what is the zone of a line L, and what is the complexity? That's what I'm going to explain in the next video.